Decentralized networks operate on a strict axiom. For the system to function, individual nodes must successfully establish direct bilateral communication to process requests. In the real world, a physical barrier stands in the way of that direct connection. The vast majority of consumer hardware operates behind network address translation, or NAT, firewalls. By design, these home routers act as a strict shield, automatically blocking any unsolicited inbound network traffic to protect the user from external threats. Historically, peer-to-peer networks bypassed this blockade using a brute force workaround known as hole punching. This probability-based model assumes that if enough nodes try to connect at exactly the right time, some will succeed. But operating at scale across diverse hardware environments introduces unpredictable failure modes. When a data network relies on randomized success rates just to maintain its transport layer, achieving high reliability performance becomes impossible. A network cannot scale if its core architecture relies on timing-dependent router hacks rather than stable engineering. Autonomi pivoted from stochastic hole punching to a deterministic MASQUE relay system. Reliability, finding correct nodes, jumped from 40% to 100%. These gains meant speed. 50 megabyte uploads dropped from 8 minutes to under 2, and downloads finished under 60 seconds. Two specific software upgrades drive these metrics: the implementation of MASQUE relays at the transport layer and the enforcement of strict iteration budgets during node routing. Together, these solutions take the burden of connectivity away from the user's restrictive home hardware and place it directly onto the network protocol. Replacing probability-based routing with deterministic logic allows distributed networks to bypass legacy NAT restrictions by design. Understanding the failure of the legacy system requires looking at the mechanical dance of a hole punch. Success requires precise synchronization. Both nodes must initiate outbound requests at the same time to trick their respective routers into opening a temporary port. If there is even a microsecond of delay on either side, the router's temporary window snaps shut, rejecting the inbound packet. This desynchronization results in a connection failure, forcing the nodes to restart the process. Compounding this is the hardware itself. Different router manufacturers employ varying protocols, meaning they handle these simultaneous outbound requests in unpredictable ways. Across a global map of interacting nodes, these microscopic hardware-level rejections compound, dragging down the reliability of the entire network. Hole punching remains unreliable because it delegates core network stability to consumer hardware that the protocol cannot control. The MASQUE relay protocol resolves this by restructuring how inbound data is handled from the first principles. Instead of attempting simultaneous breaches, a NAT-bound node now establishes a single, persistent outbound connection through its firewall. It locks this outbound connection into its nearest publicly accessible node. This specific locked connection creates a persistent MASQUE tunnel. Because this tunnel was initiated from the inside, inbound network traffic can now avoid the private router's firewall entirely. All external traffic destined for the node hits the intermediate public node instead. The public node then passes the traffic deterministically down the already open tunnel. This allows the node to participate in the network without ever needing to punch through its own router. Relying on a stable, open tunnel mathematically eliminates the timing games required by legacy hole punching. This mechanism is entirely distinct from the relay systems used in the 1.0 architecture. It is used only when a direct connection is physically impossible. MASQUE achieves consistent connectivity by shifting the routing burden from restrictive home firewalls to the network's public infrastructure. Beyond reliability, the legacy hole-punching architecture contains an inherent privacy vulnerability. For hole-punching to work, both communicating endpoints must see and synchronize with each other's true home IP addresses. The MASQUE relay architecture changes this bilateral exposure. Because traffic routes through the public relay node, peers only ever interact with the relay's IP address. The home node's direct identity remains hidden. By routing through an intermediate point, node identities are masked from their peers as a structural byproduct of the connection logic. While the transport layer fixes the physical connection, the network also required optimizations at the software logic layer, specifically during the quoting phase. The quoting phase is the process where a client queries the routing table to find the correct nodes to store or retrieve data. This visual routing table demonstrates a specific latency trap that was slowing down connection speeds. The system was frequently dialing stale port addresses for nodes that had disconnected and reconnected elsewhere. Every failed dial incurred a massive penalty, a hard-coded 15-second timeout delay before the system would move to the next address. The fix involved implementing tighter dial timeouts and enforcing smarter iteration budgets. Now, the system rapidly cycles through the routing table, discarding dead ports instantly and finding valid connections without the cumulative delay. These updates show that unoptimized software loops can bottleneck a network just as severely as restrictive physical hardware. These underlying daemon optimizations synchronize with the desktop application. The updated interface now controls daemon states, ensuring note statuses and version numbers remain accurate in real time. This enables practical tools, like a new command calculating upload costs before data is committed to the network. The entire architecture operates on a strict operational hierarchy with built-in fallback mechanisms. MASQUE is used exclusively as a failsafe. The system prioritizes the speed of direct connections via universal plug-and-play, triggering the relay only when those paths are blocked. This ensures the fastest possible connection for any given router configuration while guaranteeing that data is delivered regardless of network restrictions. Merging the hardware abstraction of MASQUE with the logic efficiency of the updated routing table provides a stable baseline for peer-to-peer communication. While the transition as nodes upgrade may introduce brief volatility, the resulting network reliability is a permanent technical improvement. Standardizing how nodes navigate NAT removes the primary uncertainty for developers building applications that require consistent node availability. Removing these hardware-specific barriers allows the protocol to function as a reliable storage layer, independent of the user's local network environment.